Now, in this video, we'll see some definition to understand these simple harmonic motion terms easily. So, first definition is complete oscillation. What is complete oscillation? Complete oscillation. So, what is complete oscillation? This complete oscillation says that an oscillation is said to be complete if vibrating or oscillating object starting from a point returns to the same point along the same direction. So, suppose we take an example of simple harmonic motion, a sine wave. A sine wave, or we can say this is also a sinusoidal wave. Sinusoidal wave. Okay. So this wave starts from this position O in that manner. Okay. So we take some point O, A, B, C and D. Now, what is our complete oscillation says? It says that an oscillation is said to be complete if vibrating or oscillating object is starting from a point returns to the same point. So, starting to a point and returns to the same point. Then we can say this whole oscillation is known as complete oscillation. Here we can see that at that O position our sinusoidal wave is starting. Okay, and this direction is upwards, and this A position our sinusoidal waves are in the same position. O and A are the same position, but that direction is downwards. But in the B position our O and B are at the same position, and its direction is also in the upwards direction. So this OAB, this is known as our complete oscillation. This OAB is known as complete oscillation. Okay, so this is our first term we have to understand. Then our second term is time period. What is time period? Time period. Okay, so what is time period? So it says that time taken for a complete oscillation is called time period. So time taken for this wave from O to B is known as our time period T. This is known as our time period T. And what is frequency? Then another term is frequency. This frequency says that the number of oscillation completed by a particle in 1 second is called its frequency, and it is denoted by F. So it says that the number of oscillation completed by particle in 1 second. In 1 second, how many oscillation it is done is known as frequency. There is a relation between this time period and frequency, which is T is actually equals to 1 by F. So this is inverse relation between time period and frequency. Okay, I have understood this. Then the fourth term is amplitude. Amplitude. So it says that the maximum displacement of the vibrating or oscillating object on both sides of the mean position is called its amplitude. This is our equilibrium position or our mean position. Okay, and this two distance, suppose this d1 and this is d2, and this d1 are actually equals to d2, and this displacement or this distance is known as amplitude. So what is amplitude? I hope you understand this thing. What is amplitude? This amplitude says the maximum displacement or of the vibrating or oscillating object on both sides of the mean position is called this amplitude. There are two types of amplitude. One is linear amplitude. Linear amplitude, which is denoted by A, and another one is angular amplitude, which is denoted by theta. Angular amplitude. Then our next term is phase. Phase. So what is phase? So it says that the state of motion of a vibrating particle. So it is a state of a motion, state of a motion of vibrating particle. So what is the state of motion? What is the state of motion? It says that at any instant is called this state of a motion of vibrating particle at any instant is called its phase at that instant. So state of motion of vibrating particle at any instant is determined by its displacement. How we can determine its phase? It is the state of its phase is determined by displacement, okay, or velocity and acceleration So at any instant this displacement, velocity or acceleration is the state of its motion, and this state of its motion of vibrating particle at any instant is known as the phase of this particle at that instant. Okay, so phase is the only quantity which continuously increase with time. So it is always increasing with respect to time. Okay, so I hope I understand this 5 definition, and this 5 definition will be helpful towards to our next part of this video. Now let us see some expression of displacement, velocity and acceleration of a particle executing simple harmonic motion. Okay, suppose this is a circle, this is the center of this circle, and we denoted some point. This is B point, this is C point, this is D point, and this is E point. Suppose the amplitude, or not this amplitude, suppose the radius of this circle is A. Suppose the radius of this circle is A. So we can say, let a particle move round a point O in a circular path B, C, D, E, okay, of a radius A at an angular velocity omega, and this our angular velocity is omega. So let it time t, so sometime t to point P from point C. So our particle is moving this point C to point, suppose we denoted this point as P. Okay, suppose our particle is moving from C to P. So now we draw a normal on this OB line, then I will get PN. This is the, so we can say that OB is perpendicular to, or not OB, PN is perpendicular to our line OB, and when it comes from C to P, it creates an angle of theta. This is our angle of theta. As these two lines are parallel to each other, as this is theta, that will also be a theta. Now our particle at first is at point C, our particle at first is at point C, which is actually in this OC line. And when it's come from C to P, what is the linear displacement? So the linear displacement is this particular displacement. So we denoted this displacement is x. Okay, we denoted this displacement is x. So now we have to calculate this displacement. So we have to calculate the displacement first. So our displacement x will be still equals to, now take the triangle OPN, and if we use the formula of sine theta, then I will get sine theta equals to ON by OP. Okay, ON by OP, or we can say that ON is actually equals to OP sine theta. Then we know the value of ON is a displacement which is we denoted by x, and the OP, our radius of our this circle is a. So I can write this thing as a equals x equals to a sine theta. So this is the displacement of this particle moving from C point to P point. So this is the equation for our displacement theta. But here is an there is a relation between this theta and this omega, or this angular velocity, which is actually equals to theta is actually equals to omega t. So instead of theta we can write is x is actually equals to sine omega t. So this is the equation of a displacement for our simple harmonic motion. So this is the displacement equation of our simple harmonic motion. We denoted this equation as equation 1. So we just figure out the displacement. Now what is the velocity? We know if I differentiate this displacement with respect to time, then I will get the term velocity. I know the equation of this displacement. Then if I differentiate this displacement with respect to time, then I will get, okay, there is another term I just missed, which is actually equals to the radius a, or we, in that case this a is represent our linear amplitude. I just forgot to write this thing a. Then I will get sine omega t. Then it will be actually equals to a omega cos of omega t. So this is the equation of our velocity v of this particle moving this CBED path. Okay, I hope you understand this thing. Then what is the acceleration of this particle? The acceleration of this particle will be the derivation of our velocity with respect to time. So if we, as we know, the velocity term of this particle moving this simple harmonic motion path, so what will be the acceleration? If I differentiate this thing with respect to time, then I will get the value of acceleration. So which will be equals to actually a omega cos of omega t. Okay, if I differentiate this term, then I will get a omega square minus sine omega t. Or we can write this thing as acceleration a is actually equals to minus of a sine omega t minus of omega square a sine omega t. What is this a sine omega t? Is actually represent our displacement. Then I can write this thing as a is actually equals to minus of omega square x. Okay, so this is the term of our acceleration. So in our first video we discussed that our acceleration when a body is moving in simple harmonic motion, or a particle moving in, or object moving in simple harmonic motion, its acceleration is actually proportional to the displacement, and this acceleration is always acting towards its mean point. So there we use a minus sign. So from this, if this omega, or this this angular velocity is constant for this particle, then I can say this thing as a is actually proportional to minus of x. So I found this thing, the condition for simple harmonic motion is actually matching the formula we just derived from this circular motion. So I can say this motion of this particle, or this particle is a simple harmonic motion. I hope you understand this concept of simple harmonic motion and these three terms of this simple harmonic motion. We actually need this displacement, velocity, acceleration, all of this term for solving maths problem or solving or some differentiate or to provide differentiate equation of our simple harmonic motion. Okay, as one more thing I should add, this thing is, we know our displacement is x equals to a sine omega t. If there is some phase difference, then we know we represent our phase difference is del. Then we will add this del with our omega t. Then our displacement equation will be look like a sine omega t plus of del. Why del represent our phase difference. Phase difference. Okay. So when we solve math equation or math problem, then we will see why this phase differentiation is actually important. Okay, so that's all for today's video. Please like this video and do subscribe to our channel. Thank you.